Hello and welcome on the next lecture on Introduction to Theoretical Computer Science. On the last week we started to discuss computational complexity of algorithm, and we have concentrated mainly on time complexity. So today I will add some additional remarks concerning computational complexity of algorithms. So at first I will shortly mention also space complexity, which analyzes how the amount of memory that must be used during the computation. The first question is what should be the units in which we should measure the size of memory, of used memory. So one possibility would be to consider, for example, number of bits we need to represent configurations of during a computation, or another possibility would be to consider some kinds of memory cells if the memory was organized this way, where each memory cell could contain, for example, one integer or one pointer to memory and so on. And if we would define what's the size of what's the amount of memory used in a given configuration somehow, then for each computation of a machine we can take those configuration where this amount of used memory is biggest. And this would be the amount of memory used during this particular computation. So then, if you remember, as we defined the time complexity in the worst case as a function that to a given size of instance of the problem assigns the maximal running time of the algorithm on the instances of the given size. So in case of space complexity, it's very similar. The space complexity of algorithm is formally a function that to a given given size of the instances considers all computations of the instances of the given size and takes the maximal amount of memory used in these computations. So if we denote this function as, so Sn would be the maximum amount of memory used by the given machine performing the given algorithm on inputs of size n. I just return to the units in which we would measure the size of the used memory. I mentioned in one possibility, this more abstract view is to consider that we have some abstract memory cells that can store integers or pointers and things like that. This measure of the size of memory is reasonable in the case when the values which are stored in these memory cells are rather small. They will basically, if they would correspond, for example, to the situation that we have in real programming languages, in real implementations, where we, for example, have integers or pointers are for example 32 bits long or 64 bits long or something like that. So of course in the general mathematical definition we do not to put such artificial restrictions like 32 bits or 64 bits or something like that. So we do not put we typically do not put some bound on the size of things that could be stored in this memory cell, but they shouldn't be very big, because in that case or if we would allow in the model to store in memory cells some big values, then probably the better measure of the size would be to consider the total number of bits. If we would allow, for example, to store numbers that could have thousands of bits or something like this, so then in the analysis would be more reasonable to consider the number of bits as the size of which is required for the given value. I just mentioned some relationship between the time complexity of algorithm and a space complexity. So of course, for the same problem, it could happen that there could be algorithm which is more efficient in terms of time, and some other algorithm that is more efficient in terms of space, of amount of memory used during the computation. Because for example, there could be some efficient algorithm that can use quite a lot of memory. For example, if they store some computed values and reuse them during computation and use this to save the total time. Or there could be some other algorithm that could be more memory efficient, that would store only things that are strictly necessary, that cannot be recomputed, and whenever it needs some value that could be recomputed, it recomputes it once again, even if it's used several times, and so on. Yeah, so we can easily imagine that the fact that one algorithm is more time efficient does not necessarily mean that it's also memory efficient. In fact, it's often the case that these two requirements are often rather in conflict. That we can spare some time using more memory, or we can spare some memory if we use more time of computation. But if we consider just some one particular algorithm of for the given problem, and consider its time complexity and space complexity, so under almost any reasonable definition, it's the case that this space complexity cannot be bigger than this time complexity, assuming that in every step performed during the computation they are used only maybe some constant number of memory cells is used. That of course this depends on the particular definition of the computation model of the machine that performs the computation, but in practically all reasonable models, it's the case that and definitions of time complexity and space complexity, it's the case that only some finite amount of memory is used in each step. And also, if we assume that we do not have model that would allow to allocate big amounts of memory without using this memory, without accessing the cells of this memory, of this allocated memory. So if we assume the algorithm does not work like that, that whenever it allocates something, it really reads and writes to the allocated cells. So it's quite obvious that the total amount of memory used by the algorithm cannot be bigger than the running time of the algorithm. But of course, the amount of memory could be smaller than the running time. If you remember, as we analyzed, for example, insertion sort algorithm, and we came to conclusion that its time complexity is in theta n square, but its space complexity is in theta n. Because if we count the number of cells of the array, this is probably the main part of memory used by this algorithm. So if the number of elements in this array is n, so it requires n cells for this array, and it also requires some additional cells to store some local variables, like the size of array and some indexes pointing to arrays, and possibly some local variables to store the values which are read from arrays that are currently processed and so on. But there is only some constant number of such memory cells to store these variables, and they are negligible with respect to the size of the array when the n is big. So it's quite obvious that the space complexity is in theta n in this case. So this was about the space complexity, and let's return back to the time complexity, and we have defined theoretically what it means that time complexity is in, for example, big O n square or big O n to 3 and so on. But what I would like to mention now is to give you some intuition what it means in practice, that when we have some algorithm and we analyze its complexity and derive some particular time complexity. So of course this result does not necessarily mean some precise bound on the real running time, I mean in seconds or milliseconds and so on, because in this asymptotic notation there could be hidden some constants. But assuming that we have some reasonable implementation that where in the analysis we are not hidden some big constants, some usual algorithm, and let's assume we would run these algorithms on some standard or usual PC, usual desktop computer or usual notebook, and let's think about how big inputs could be typically processed on such a usual computer, could be processed maybe in seconds or several seconds or some fraction of seconds. So at most several seconds, so it will not take, for example, minutes or hours. Typical sizes of inputs that could be processed on today's computers, and again we assume some standard computer, not some supercomputer, some very very powerful machine or something like this, some standard computer everybody could have. So if we have algorithm with complexity in big O n, so with linear complexity, so in this time of second or several seconds we could easily process inputs of size such as 1 million, from 1 million maybe to 100 of millions. So rather big inputs could be processed quite fast by this algorithm. If we have complexity like n times log n, big O n times log n, which is a complexity of those more efficient sorting algorithms, for example, like merge sort or heap sort, then we can process inputs of size like 100,000 up to 1 million elements. So this can be easily processed with algorithms with this complexity. If we have algorithm with quadratic complexity, so in big O n square, so typical sizes of inputs that could be processed quite fast are from 1,000 to 10,000. If we have cubic algorithm, so with complexity in big O n to 3, so inputs of sizes like from 100 to 1000 could be reasonably processed. But if we would have exponential complexity like 2 to n or 2 to big O n, so we can, if it is really the case that this number of operations is performed for the given instance, then we could solve this problem for instances of sizes like from 20 to 30 at most, or typically not much bigger than this. And if it's something like n factorial, so in big O n factorial, so even smaller, like from 10 to 15 at most, because it grows even faster than 2 to n. Of course, we should be aware about some problems that could be connected with using asymptotic complexity, because it does not provide the whole picture, the complete picture of the situation. It can be more complicated in practice. So basically, the asymptotic notation provides information how the running time will grow when we will use this algorithm for instances of bigger size. For example, if we know that time complexity is in theta n square, so we can derive from it that when we take input of some particular size and run it for some time, and then we take input that will be, for example, 10 times bigger, so it will take 100 times more time to compute the result. Of course, because we in asymptotic notation we ignore the constants by which these functions are multiplied, so they cannot say anything precise about the precise running time, and this is something that depends on the concrete machine on which it runs, and on many details of implementation. And in some particular cases, some big constants could be hidden in this asymptotic notations in some algorithms, and it can also happen that when we have two algorithms and one of them has some better asymptotic complexity than some other, it does not mean that on each input this algorithm with lower time complexity will be faster than this algorithm with the bigger complexity, because this asymptotic notation deals with the rate of growth of functions and how they behave for big N. So it can easily happen that, for example, for some small inputs, this algorithm with greater asymptotic time complexity could be in fact faster. As a typical example, if we consider this efficient algorithms for sorting, like maybe quick sort, heap sort, merge sort, and so on. And if we consider some simple algorithm like bubble sort, insertion sort, selection sort, so of course when we would have some big input, maybe array of 1000 of elements, so these efficient algorithms will be very much more faster than this simple algorithms with quadratic complexity, these bubble sort and so on. But if we would consider some small inputs, let's say input array of with 10 elements or something like this, and if we would measure the running time, so typically these simple algorithms will be faster than these more efficient algorithms, because they are simple. So in each iteration could be implemented quite efficiently. The number of perform operations is quite small in each iteration, so the constants which are hidden in this asymptotic notation are for these quadratic algorithms could be rather small. Yeah, so for on small inputs, they will be more efficient. And another thing that we must be aware when we talk about asymptotic time complexity, and especially when we talk about the worst case complexity, is that in some cases this time it takes for more instances is not much better or not much shorter than not much smaller than the time it takes in the worst case. But there could be algorithms for which on some instances it can run much faster than the worst case. And so there can be this big gap between the worst case and how long it runs on some instances. So it could happen that on many instances on that we will run the algorithm, the real running time will be much smaller than the worst case. Yes? So again, this is not something that could be directly derived from some asymptotic estimation of the complexity in the worst case. So in some cases this could be more complicated. The typical example of this is a quicksort. Yeah, where in the worst case the running time could be n square, and in the average case it's n times log n. Yeah. So here again I will give I as an example I will present a comparison of three typical sorting algorithms, that solve the problem of sorting an array. Yeah, so one type of algorithms are those very simple algorithms like bubble sort, insertion sort, and so on, that have the complexity in the worst case is in theta n square, and in average case is also in theta n square. So these algorithms, these simple algorithms, are typically very efficient only on small inputs. But with growing n, they are much worse than the other types of algorithms. There are algorithms like heap sort or merge sort that have complexity in the worst case or in average case. In both cases is in theta and log n. Yeah, so the average case is not worse than the worst case, and but there is this interesting example of quicksort, where typical straightforward implementation of quicksort has time complexity n square in the worst case, because I just recall, if you remember how quicksort works, the idea is that we somehow select some element in the array which is called pivot, and we compare with this pivot, we compare each element in the array, and we move those elements which are smaller than pivot, we move it to the left part of the array, and those that are bigger than pivot, we move them to the right part of array, and pivot is put between them, and then we run the quicksort recursively on these. So this way this array is divided into two parts, where in the first part we are sure that there are those values that are smaller than pivot, and the second part is the part where the elements are bigger than pivot, and we run recursively quicksort on these parts of the array separately on each of them. Yeah. So of course, when we are lucky and we select some as pivot some element which is approximately in the middle in the sorted arrays, so approximately 1/2 of elements will be on one side, and approximately 1/2 of elements will be on the second half, and if in every recursive call of this procedure we it would happen approximately the same. So then the total time could be shown to be something like n times log n. But there could happen the worst case that we have bad luck, we are unlucky, and we choose as a pivot some element which is, for example, maximal value in the array. Yeah? So when we compare all other elements with the given value, so this one part will contain all remaining n-1 elements, and the other part of those bigger than this element would be empty. Yeah. By the way, it's quite obvious that this if we choose this pivot somehow, and if we compare all these elements in the array with it and move them to these two parts, so all this can be done in theta n in linear time. So let's consider now this left part again, and again we would have bad luck, and we would select again the maximal value in this part. Yeah. So again, all these elements, we will divide this part to those that are smaller than this, and to empty part that are bigger than this element, and so on. Yeah. So we will n times we will perform this recursive call, and in every step, if we would have this bad luck that the maximal or minimal value will be selected, so it's clear that the total time that is spent in that is approximately in n square. Yeah. So in the worst case, quicksort basically is not better than bubble sort or insertion sort and other simple quadratic algorithms. But in most cases, and it can be shown that in fact, if we take the average time, how long it takes, so even if not every in every recursive call we will be lucky and select some element in the middle, it's sufficient that it occurs sufficiently often. So in most cases it will happen that in fact the time will still be in n times log n, and that these cases where these quadratic behaviors occurs they are quite rare in the input, yeah, but in between the possible inputs. And it's interesting that in practice, when we will generate, for example, some random data and test these algorithms on them, so typically quicksort will be faster than heapsort, because the constants which are hidden in these asymptotic notations, yeah, because quicksort is quite simple. The most time is spent by moving this and comparing these elements and moving them to this first and second half on the given part of the array. So this is quite simple operation that could be implemented quite efficiently. Yeah? Algorithms like heapsort and mergesort, they are more complicated. They perform each iteration more work. Yeah. So typically quicksort will be slightly faster than heapsort or mergesort. Yeah, but of course they are considered. It depends how the pivot is chosen. Yeah? If we use some naive choice that, for example, we will always take the first element in the given part of the array or something like this. So it would not be too difficult to construct example of instance on which this quadratic behavior occurs. But there are some more clever ways how to choose the pivot. Where in fact it could be rather difficult problem to have some way how to construct examples of these instances for each n. for which this bad behavior occurs. Yeah, so this was the illustration of some issues that could be connected with the use of asymptotic complexity, and just a warning that in practice situation could be often more complicated than what is captured just by asymptotic complexity in the worst case or average case. I have before, maybe I have already mentioned what does it mean that some time complexity or space complexity is polynomial. So I will now say a few words about polynomial time complexity. So at first, what we mean by polynomial. Yeah? So formally, polynomial function, especially when we will concentrate on polynomials with one variable only. Yeah? So these are those functions that could be expressed in the form that there is some constants times 2n to k plus some other constants times 2n to k minus 1 plus 2 another constants times 2k minus 2 and so on. So typical example of a polynomial is something like this. Yeah, this is a constant times n to some constant minus 2 times n to 2 plus 8 times n to 1 plus 13. Yeah, so this is one example of a polynomial function. This is another example of polynomial. This is another example, and to 100 is another example of polynomial. So we call a function polynomial if it's bounded from above by some polynomial. Yeah? If we use it not strictly only in this sense, but we call a function polynomial if we could bound it from above by some polynomial. So formally we mean that f is called polynomial if f belongs to big O and to k, where k is some constant. Yeah, so typical polynomial bounds are there are several examples. Yeah, because for n it's quite clear, but for example n times log n is strictly speaking it's not a function of this time, but it could be bounded from above by such polynomial. Yeah? It grows. It could be bounded from above, for example, by n square. Yeah, so in this sense it's polynomial. Yeah, of course, when we have some constant like 2, 5. Also, square root of n is a polynomial, yeah, because it's the same as n to 1/2, and of course something like n to 100. Yeah, so this is what formally we mean when we talk about asymptotic complexity of some algorithm, and when we say it's polynomial, that it's bounded by some function of the form n to k, where k is a constant. Typical examples of functions which are not polynomial are functions 2 to n or n factorial, where it can be shown that for arbitrarily big n to k is 2 to n belongs in omega and to k. So in fact it grows faster than any polynomial. And the same case it's for n factorial. So they cannot be bounded from above by any polynomial. Yeah? There is no fixed constant k such that this function could be bounded from above by this polynomial. So we call those algorithms whose time complexity is polynomial. So we call these algorithms polynomial. Yeah, so they, if their complexity is bounded from above by some polynomial, and these problems or these algorithms which are polynomial are, roughly speaking, they could be considered as as efficient algorithms. Yeah, that they are efficient in practice in the sense that they could process big inputs in reasonable time. Of course, this is just some approximation to the reality, because of course, by this definition, it would also mean that algorithms with time complexity like n to 100 would be considered efficient, which is obviously not the case. Even for small values of n, n to 100 would be some very big number. Yeah, so such algorithm would not be useful in practice for rather small instances. It can also happen that depending on what requirements we have, how big inputs we want to process and in what time, it can also happen that even algorithms, even polynomial algorithms, like quadratic algorithm, could be unreasonable in practice when it does not meet the some time requirements we would have on the algorithm. So for some purposes, even quadratic algorithms could be too inefficient. And it can also happen that for some problems, even problems with exponential complexity like 2 to n could be reasonable for the types of instances for which we want to solve it. If we want to solve it for some small instances, or if we solve it for those instances on which it runs much faster than 2 to n. So it can happen that even those algorithms that are exponential in the worst case could be still useful in practice. So in this sense, this is not some strict bound, but on the other hand, it's quite useful approximation of what could be considered efficient. I have already mentioned that, of course, algorithm with time complexity in theta n to 100 is not very useful, and but it's the case that for problems that we typically want to solve in practice, it's not the case that we would have some algorithm with time complexity n to 100 and we would not have some algorithm with smaller complexity. In theory, it's possible to artificially construct such problems for which could be solved by algorithm with time complexity n to 100, but cannot be solved by any algorithm with time complexity n to 99 or something like that. But these are artificially constructed mathematical problems, and this typically does not occur for kinds of problems we want to solve in practice. In practically all problems that are studied and solved in practice, it's the case that either we do not know any polynomial algorithm, or when we know some polynomial time algorithm, then we know polynomial time algorithm with rather small degree of the polynomial. So typically something like maybe at most 5, but typically 4. Maybe n square, n to 3, n to 4, n to 5. In some cases, it's slightly bigger, but it's typically not the case that would be some much bigger number than this. So and as I have already mentioned, we could have some algorithms which are not polynomial, but can still be useful in practice on many inputs, especially if they are implemented in some clever way, and they are not, if there are no these stupid kinds of these kinds of brute force kinds of exponential algorithms that just try all the possibilities, but if they do it in more clever way, so it can still happen maybe for such algorithm that they could have inputs for which exponential running time could happen for some inputs, but on many inputs these algorithms could be more efficient. So as I have mentioned, for most problems where a polynomial algorithm is known, then it's the case that some polynomial with small degree is known, like 5 or 3. So when we have some typical problems that are studied from algorithmic point of view, for which algorithms are constructed, so this is one situation that could happen, that for the given problem we have some rather efficient polynomial time algorithm with rather small degree of polynomial. Or the other possibility that could often happen is that there is no known polynomial time algorithm in the worst case. So every algorithm has, in the worst case, some exponential complexity, and in some cases we even have proofs that such algorithm cannot that polynomial time algorithm cannot exist. But what is also quite very common is that there is no known proof that polynomial time algorithm cannot exist. I will discuss these things in more detail later. So this is another possibility, that we have some algorithm, that it's obvious that we have an algorithm for the given problem, and that the complexity of the algorithm that it's quite often quite straightforward to have exponential time algorithm, but where no efficient polynomial time algorithm is known for the cases. So this is the second possibility that often occurs in practice. And another thing that could also happen, as we will see later on the next lecture, is that there are some problems for which no algorithm is known, but what is more interesting, that there are problems for which can be proved formally there cannot exist any algorithm that would solve the given problem, in the sense that for every input it will be ensured that the algorithm will halt after some finite number of steps and give a correct answer for each instance. So there are even problems that cannot be that could be formulated precisely in mathematical terms, but for which it can be proved that there cannot exist any algorithm that would solve the given problem. Let's return back to the analysis of complexity of algorithms, time complexity of algorithms, and let's take a few examples on which we will illustrate how we can analyze the complexity using asymptotic notation. So there are some simple cases, like the straightforward algorithm for multiplying matrices. Let's for simplicity consider here square matrices, each of them of size n times n, where A and B are the matrices we want to multiply, and the C will be the matrix where we will store the result of this multiplication. And if we use the straightforward algorithm that computes this resulting matrix, so it basically consists of 3 loops, 4 loops, each of them going from 1 to n, assuming that indexes in these matrices of these rows and columns go from 1 to n. it's clear that the most often performed part of the algorithm is the body of this inner loop, inner loop here, and the number of times how many times it's performed is n to 3. Yeah? So time complexity is obviously n to 3, and space complexity is n square, because each of these 3 matrices requires n square elements, or has n square elements. So the number of cells, memory cells used by this algorithm is something like this. We also need some memory cells to store values of n, I, j, x, k, and the things but this amount of memory used by these variables is negligible with respect to the amount of memory that we need for the matrices. Yeah? So the total space complexity is theta n square. So this is the rather simple case. We have 3 loops, which are, this loop is inside this loop, and this loop is inside this loop, so we just multiply n times n times n, so it's n to 3. But it's often not the case, and here it is, because it's the loops go from 1 to n always, or they are performed n times. So in this case we can just take the number of loops, how many loops is included in how many loops are included in each other, but the number of nested loops, and this just would give us the degree of polynomial, but it is not the case in general. When the number of iterations somehow depends on the input, or if it changes during the computation, and if it's not performed n times, so we cannot just generally say that complexity is n to 3 or n to the number of nested loops. Yeah, so we have already seen on the last lecture, when we analyzed insertion sort, where the number of iterations of the inner loop has changed with each iteration of the outer loop, and it led to some computation of some arithmetic progression. This happens quite often in the analysis of time complexity of algorithms, that basically, to compute the more precise estimation of the running time, of course we can do some rough estimation if we are quite sure that none of loops will be performed, for example, more than n times, and we would have 3 nested loops. So it's clear that from where we have this upper bound, that the real time complexity is in big O and n to 3, for example. But if the real number of iterations could be smaller, then in fact the real complexity could be smaller. Yeah, it was not the case in the case of insertion sort. We have just 2 loops, and even if the inner loop was performed smaller number of times than n in each iteration of the outer loop, so still the total complexity was n square. But in general it can be more complicated. Yeah, so this often could lead to the computation of some sums of progressions, and 2 most often occurring cases are arithmetic progression and geometric progression. So I just recall that arithmetic progression is some sequence of numbers, let's know them A0, A1 and so on, where AI is computed as A0 plus I times D, where D is some constant. Yeah, so basically it means that the difference between each pair of consecutive elements, between a0 and a1, between a1 and a2 and so on, that this difference is always the same. Yeah, so always ai plus 1 is equal to ai plus d, and this is sum that is a quite simple way how to compute this sum. We just take the first and the last element in this sequence, add them together, yeah, so a(n minus 1 plus a0, and multiply it by the number of elements, and then we will divide the result by 2. So this gives us this sum. Yeah. To see that this is the case, just imagine that we would write this sum, that we would take this sum 2 times. Yeah? If we would compute the sum of 2 copies of this sequence, yeah? So then if we would compute this, we would just divide by 2, which is this multiplication by 1/2 or division by 2. Imagine that we would write one sequence in this order and the second sequence in the opposite order, and you can check that if we add this first element with this first element in the second copy in this reverse copy, yeah? So it will be the sum of the first element in the first copy and the second element in the last element in the second copy, the second element in the first copy, and the second element in the second copy, this reverse copy, which would be next to us element, and so on. Yeah, so we will have n such pairs, and we can easily know that the sum of these pairs is always the same. The sum of each such pair is the same. So we can just take the first pair, and we have n such pairs. Yeah, so this way we could derive this sum. Yeah. So in particular, the very common case of arithmetic progression is when this d is 1. Yeah. So if we want to compute the sum from 1 to n, yeah. So if we use this expression, so we will obtain something like this, which when we use asymptotic notation is in theta n square. Yeah, so for example, from 100, the sum of from 1 to n is 1/2 of times 100 times 101, which would be 5050. Yeah, so here is this example, yeah, that 1 plus 100 plus 2 plus 99 and so on. Yeah, so this was the arithmetic progression. And for geometric progression, where again we have some finite sequence where each element is element ai is computed as a0 times q to I. So it means that the next element is always computed from the previous one by multiplying by some constant q. So the case where if q is 1, so it would just mean that if we multiply by 1, so all the elements in the sequence are the same. So we would just multiply the number of elements in this sequence times the value of the element of each of the element. And in the case when q is different than 1, so there is again a way how to compute it using this expression. So for example, if the value of a0 is 1, so this sum from 1 plus q square plus q to 3 and so on could be computed like this. So in particular, for example, if q is equal to 2, so we would obtain this. So here we have 2 minus 1 is 1. Yeah, and this could be written as 2 times 2 to n. So we can see that this is something which is in theta 2 to n. It's quite often happens that that some functions we analyze in time complexity or space complexity and so on, they are quite often are polynomial, and other kinds of functions that often occur are exponential functions and logarithmic function. So I will record that exponential function is a function of the form of c to n, where c is some constant, yeah, like in 2 to n, and logarithm is an inverse is the inverse function for exponential function. Yeah, so logarithm of n with base c is a value. The value of this is some such x such that c to x is equal to n. Yeah, so for example, if c is 2 and n is 1024, so the question is to which power of 2 I must take to obtain value 124, and this is 10. Yeah? So here is a table illustrating the values of exponential function for different values of n. So we can see that exponential function 2 to n, it grows quite fast. So even for small values like 20, the value of 2 to n is about 1 million. And the logarithm of n is which value which power of 2 we must take to obtain the given value of n. Yeah, so we can see it grows quite slow. It's even more. We can see it if we consider this these powers of 2 as values of n. Yeah, so for quite big values of n, we have quite small values of logarithm. Yeah, so for example, for 1 million, so it's approximately approximately 20. So typically, so as we can see, logarithm is grows much slower than n. Logarithm of n is typically much smaller, and the difference is bigger and bigger, especially for big values of n. And so now we have some idea how fast exponential function grows. Yes, so exponential functions grows rather fast, and logarithms grow rather slow. I will mention also one property of logarithms, maybe. That you have may notice that sometimes I have omitted the base of the logarithm. Yeah, I have written just logarithm of n in use of asymptotic notation. So of course, in general, the base of the logarithm, if we want to compute the precise value, so the base of logarithm is important. This value of c is important for the precise value. So logarithm of n with base 2 will be different than logarithms of n with base 10 in general, but these logarithms are quite closely connected. It's not difficult to show that if I want to compute logarithm n with base a, so and if I would be able, for example, to compute logarithm with base b, so this logarithm could be computed like logarithms of n with base b divided by logarithm of a with b. Yeah, so assuming this a and b are some constants, so basically 1 divided by logarithm of a with base b would be a constant. So we can see that now this logarithm of n with base a and with logarithm of n with base b are linearly connected. They differ only by multiplying by some constant. So in the case of in the use of asymptotic notation, it makes no difference if we would have logarithm with base 2 or base 10 or base 77. It would still be the same from the asymptotic point of view. So it's quite common to omit this base, and we just assume that the base is some number which is greater than 1. To derive this, it's quite simple. Just from definition of logarithm, it must be the case that if I take a to logarithm of n with base a, so by definition it must be equal to n. Definition of what logarithm means. And then if I have this equality, then I can take logarithm of both sides, logarithm with base b. So I would have this, and it's well known that if I have logarithm of some x to y, so it's equal to y times logarithm of x. So using this transformation, I can transform this part to this. I can take this exponent before in front of the logarithm, and so this could be rewritten like this. So if I have that this is equal to this and this is equal to this, so we have this equality. So if I now multiply both sides of this equality by 1 divided by logarithm of b with logarithm of a with base b, so we obtain this result. So this is just recalling the transformation between logarithms, and that the real base is in case of asymptotic notation is in fact not important. So I will now give a few examples of typical cases of algorithms where such things like exponential or logarithmic functions can appear in the analysis. Logarithms will often occur in case where we decrease size of something by dividing it, for example, by 2. Typical example of such algorithm is a binary search, when we have a sorted array and we have an element we are searching for in this array. So we choose some element exactly in the middle of the array and compare the search element with it, and if it's smaller or bigger, so depending on it, we consider the first half of or the second half on the array, and we proceed in the way. So each iteration, the size of the search interval is divided by 2 approximately. So if we would like to, so the total time of the algorithm is basically determined how many by it how many iterations. In each iteration, the size of the interval is divided by 2. So if we start with interval of size n, so how many times how many iterations we must do to obtain interval of size 1, where that would correspond to the search. Or where the either we have found the element or have not found. If we compare in interval of size 1. So this question can be reformulated as follows: that instead of how many times I must divide n to obtain value 1, would be to ask, if I would have some fixed k and the algorithm performs k, if I know that the algorithm performs k iterations, so question is what's the minimal value of n, the size of the array, that I would have at least k iterations for given a value of a. and it's probably no difficult to see that for one iteration size 1, for 2 iterations size 2, for 3 iterations size 3, or something like this, that the size is approximately exponential, with respect to the number of iterations. So if we take logarithm, so if n is approximately 2 to k, so if we take logarithms of both sides, we would obtain that k is approximately logarithm n. So the time complexity of this algorithm is theta log n. Is logarithmic. So for quite big values of n, array with 1 million of elements, it will take just about 20 iterations. Another examples where exponential or logarithmic functions occur. For example, if we work with n-bit numbers, so using n bits, using the standard binary representation, it's possible to represent, if we consider just non-negative values, so values from 0 to n minus 1 could be represented. So for example, using 16 bits, we could represent numbers from 0 to 65,535, and so from this we can derive the minimum number of bits which are sufficient to using this standard binary representation of numbers. The minimum number of bits that are required to represent number x is something like this. This is a logarithm of x plus 1 rounded up. Another typical examples where we have exponential and logarithmic functions is in the analysis of some algorithms that work with trees, maybe some balanced trees. So so let's consider a binary tree for simplicity, where each node has 2 children, each node except the leaves of the tree, and let's assume for simplicity that all branches are of exactly the same length. So it's clear that if we take these layers of this tree, if we divide these nodes of the tree into the layers according to the distance from the root, so we have just one root, which is 2 to 0. It has 2 children. These 2 children, they have four children. 2 to 2. These 4, they have 8 children, and so on. So each layer has 2 times bigger number of nodes than the previous one. So if the height of the tree, where the height we consider the length of these branches in the root, if h is the height of the tree, so a layer in depth h, so if this would be depth 0, depth 1, depth 2, depth 3, and so on, so there would be the number of nodes in depth h would be 2 to h, and this forms a geometric progression. We discussed this geometric progression here. So when we use this this formula to compute this sum, so is 2 to h plus 1 minus 1. So in fact, approximately one half of all nodes of the tree are the leaves in this balanced tree, and so this is the total number of nodes, and this is the number of leaves. if we would, on the other hand, would know that we have n nodes, and we would like to know what is the height of the tree. So it's approximately logarithm of n with base 2, yeah, because this n would be equal to h plus 1 minus 1, yeah. So approximately would be something like this. So maybe this picture of such small tree like here, it could be a little bit deceiving, yeah, because it seems that there is no so big difference between the height of the tree and the width of the tree, yeah, the number of nodes here. But maybe just to give you some more illustrating picture of this big difference between because the height of the tree is approximately a logarithm of the number of nodes in the tree. Yeah. So let's consider a balanced tree where we would have 1 million of nodes as leaves. Yeah. So a tree with 1 million of nodes approximately. Yeah. So if you remember, the height of such the height would be a logarithm, so it would be about 20, yeah, approximately. So if we would draw a picture of such tree in such a way that we would separate the leaves by 1 centimeter, yeah, so 100 of nodes on each meter. So in fact the width of this picture, so of course this is not something we would do in practice, yeah, but just to imagine the width of this picture would be about 10 kilometers, yeah, for millions of 1 million of nodes. But but if we would draw it in such a way that the height of each layer would be just 1 centimeter, so the height would be just 20 centimeters, yeah. So it would be we can see the big difference between this height and between the number of nodes, yeah. So so it would be very, very flat, yeah. The distance from, if we imagine we go inside the tree from the root to some node, or vice versa, if we would start in some node and go to the root and so on. So such paths are rather short compared with the total size of the tree. As another example, consider sorting algorithm merge sort. Yeah, so the basic idea is that if we want to sort an element, so we just divide. We just take this elements and divide it into two parts, maybe in half. So we take two halves, and at first sort each half separately. So we would have so in some sense it goes in a slightly different way than quicksort. Yeah, in quicksort we at first divide, we resort elements to both parts, and then recursively solve these parts. In merge sort it's in opposite way. We at first divide some exactly in the middle. We would have two halves of the array. At first we would recursively sort these two parts, and then we should merge together these two sorted sequences into one. Yeah. So this is something that could be done in time which is linear with respect to the number of elements. Yeah. We have two sorted sequences. We could just consider the first elements in these sequences that have not been processed yet, so and compare them, and which one is smaller, then this one will be added to the resulting sequence. Yeah? So for example 10 is smaller than 34, so 10 will be selected and added. So now the first elements are 11 and 34. So 11 is smaller, so it will be added. Now 34 is smaller than 53. So from these two, 34 will be added. 42 is smaller than 53, so this 42 will be added. 53 is smaller than 58. 58 is smaller than 67. And 61 is smaller than 67. And now there is nothing more to compare, so 67 is added to the end. Yes, so this way we basically need n steps where each step consists of comparing two elements and selecting the smaller one and adding this selected element to the resulting sequence. So the main part of the algorithm looks like this, that this is a recursive procedure where we obtain an array and some range of indexes in this array from P to R, including P and excluding R. Yeah, so we assume that if at the beginning we have array starting at index 0 and ending at index n-1, yeah, so we will start with P equal to 0 and R equal to n, and in each procedure we compute where is the half of this interval. So if the length of the interval is less or equal to 1, so there is nothing to sort, because interval of size 1 is just one element, so this is already sorted. So only in case when the length of interval is at least 2, so we compute the size of this interval, and at first, so the first part from P to Q and then from Q to R recursively, and then we use this procedure merge that combines these two sequences together in this way I have described before. Okay, so this is how merge sort works. So now if we would like to analyze its time complexity, so we can imagine that this recursive procedure, it divided the original problem to sub-problems, and these again were recursively divided into sub-problems and so on. So we can imagine such tree where the elementary sub-problems were sub-problems of size 1, so and always using this merge, they were the results for these sub-problems were combined to some sorted sequences which were obtained by merging this already sorted sequences. Yes, so from these two values we obtain this, from these two values we obtain this, combining this and this, merging this and this, we obtain this, and so on. So it's clear, because the size of interval on so we have such tree where here we have at the root we have the original instance. So here what is shown here is the already sorted array. And on each next level the size of the intervals is just 1/2 of the size of intervals in the previous level. Yeah? So if I have 8, so now they are 4, 2, 1. So it's clear that the number of layers is logarithm of n with base 2. And if we want to compute the total time which is spent in the computation, yeah, so in the recursive procedure, if we would compute how much time is spent in each node of this tree, yeah, so even if it goes like this, so if we count for each node in this tree, how much time was spent there. So basically it's dominated by this merge, and it's linear with respect to the size of the given subinterval. Yeah? So but the total sum of lengths of subinterval in each layer of the tree is always n. Yeah, so the total amount of work which is spent on the given layer on this tree is in theta n, and we have logarithm n layers. Yeah, so from this it follows that the total time is n time logarithm n. Okay, so let's go now to another example of analysis of algorithms. Let's consider some graph algorithms. Yeah, so for this it could be important how the graphs are represented in memory by algorithms. So there are several possibilities. I will just illustrate two most commonly used. So let's say we would have some directed graph with nodes and edges. So one possibility is to have an array of nodes. So these nodes are somehow indexed, and each element representing a node could represent some. It could store possibly some information about the node that will be needed by the algorithm. But in particular, it will also have a list of edges that go out of the node. Yeah? So for example, for node 1 we have edge to node 2 and node 4, so we have a list containing these two edges. From state 2 or node 2 we have an edge to node 5, so it has just edge and so on. Yeah, so and maybe the particular order of edges in these grids are not important. It's also not important that I have drawn it as a list, as a linked list. But again, we could use some vectors, for example, vectors of edges, and it would be very, very similar. This. Here I have just represented the outgoing edges for each node. Yeah? For some algorithms it could be also useful to, in the same way, we could represent the incoming edges for each node. Yeah, so this is one often used possibility. Another one would be to use a matrix of size n times n, where n is the number of nodes. And this matrix would contain just, if we would not have any information connected with these edges, just information whether there is an edge or not. So in this case, this matrix would contain just zeros and ones, where 0 means that there is no edge between the given pair of nodes. That, for example, there is no node from node 1 to node 3. Yeah, so and 1 would mean that there is an edge from the node for the given row to the node for the given column. Yeah, so this 1 means that there is an edge from node 1 to node 2. There is no edge from node 1 to node 3. There is an edge from node 1 to node 4, and so on. Yeah? So and it depends on the details of the algorithm which of such representations would be which of them would be better for the given purpose. Because the difference is that here in this representation, the amount of memory used for this is linear with respect to the number of nodes plus the number of edges. Yeah, so because each node is represented just once and each edge is represented just once. So if I would have a graph that for example would have 1000 of nodes, and there would be at most 5 edges going out of each node, so I would have just 1000 of cells, at most 1000 of 5000 of cells for edges. On the other hand, here the size of this array or this matrix would be always n times n square, and it does not matter how many edges are there. Yeah, so even if there be none, so I would need n square bits of memory. But on the other hand, if the graph would be dense in the sense that there almost any edge would be connected with or almost any node will be connected by an edge with almost any other node. So for such graphs, it would be probably more convenient or more efficient to use such representation using this matrix, because this one element of this array just requires one bit. On the other hand, this cell for one edge takes several, maybe tens of bits at least. So and what could be even bigger is the difference between in the time complexity, depending on what kind of operation is performed most often. Yeah, for example, to find in this first representation, we can very fast find. It's possible to find very fast way to find for a given node the list of those edges that go out of the given loop, out of the given node. Yeah, so and the time to go through this list is just corresponds to the number of these edges, not to the total number of nodes of the graph. On the other hand, in this representation, to find all edges going out of node 3, for example, we must go through this row. Yeah, so if we would have 1000 of nodes, so it would be necessary to perform 1000 steps. So the time is linear, just to find all the edges that go out from the given node. It requires some that will be linear with respect to the number of nodes. Yeah, so even if I would have if I would have graph with 1000 of nodes, and even if the number of edges would be very small, so it would be necessary to go through this. On the other hand, if I would need to test, for example, for a given pair of nodes whether there is an edge between them, so in this fair representation it could happen that this list could be long. It could have theta n elements. Yeah, if there would be big number of edges going out of a given node, and it would be necessary to linearly go through this list. Yeah, if they would not be sorted in some particular way, or this would take time linear with respect to the number of nodes. On the other hand, in this matrix representation, it would just take constant time. We would just take a look at the particular position in the matrix and immediately obtain information whether there is an edge or not. Just to mention, sometimes we need directed graphs where edges have orientation. Sometimes we need undirected graph. It makes no big difference. Just in this representation, there is this thing that each edge is represented 2 times. Yeah, for example, this edge between 1 and 2 is one instance is here from 1 to 2, and also from 2 to 1, because we can imagine it goes in both directions. So maybe for some purposes it may be necessary to have some connection between these elements of the list that correspond to the same edge. And in case of matrix, this matrix will be symmetric with respect to diagonal the matrix. And just to illustrate the analysis of time complexity of some graph algorithm, I will describe some very simple graph, one of the most basic graph algorithms, and this is breadth-first search. Yeah? So the algorithm that finds the shortest path in a given graph starting from the given initial node S. So we assume that the input consists of a graph. It's not very important whether it's directed or not, and we will assume this first kind of representation. Yeah, so by the list of edges for each node. Yeah, so it could be either directed or undirected, and one of nodes will be selected as the initial node, and the result produced by the algorithm is that it will find a representation of shortest path for each node in the graph that is reachable from this initial node, and it will find also its distance in the terms of number of edges. Yeah, so we assume these edges are not weighted. Yeah, so we count the length of path as the number of edges on this path, and so assuming we have as input a graph with n nodes and m edges, so the total running time of this algorithm in the worst case is theta n plus m of the described algorithm. Yeah, so I will describe it in a moment. So the algorithm starts with initialization. Yeah, so we will have some arrays storing some information for each node. So one kind of information is denoted here color of a node, and the color could be white, gray or black, and the intended meaning is following. White are those nodes that have not been processed by the algorithm yet, that they have not been reached so far. Gray are those nodes that has been found, that has been found a path to the given node, but the edges that go out of the given node were not processed yet. And black color means that the node has been completely processed, and this D for each node will represent the distance from the initial node S. So at the beginning each node is white, its distance is set to infinity. After the end of the algorithm, those nodes that are not reachable from S will have still infinite distance, but those that are reachable will have some particular number that specifies this distance. And this means predecessor. This will be information that will allow to reconstruct for the given node the shortest path from S. It will be for given node U. It will represent node from which will be on the shortest path from S. What will be the last node before U, before node U. We can construct for given node the path starting from the end. Yeah, we start from U and go to the previous to its predecessor, and then to predecessor, then to predecessor, and so on up to S. So at the beginning these predecessors are initialized to nil. Yeah, they are not assigned yet for those unprocessed nodes, and the initial node S is assigned a great color that it has been found, by its edges have not been processed yet. Its distance of S from S is 0, and it does not have a predecessor. And this Q here represents a Q. Yeah, so it must be Q. So here by this I mean informally that at the beginning the Q is empty. So this is the initialization of breadth-first search, So at the beginning this queue was empty, and at the beginning S is enqueued in queue. So yes, so enqueue is some operation that adds element to the queue, to the end of the queue. And then comes the main loop of the algorithm. So by this I informally mean the test that the queue is non-empty. So as long as the queue is non-empty, so the first operation is perform each iteration of this loop is to perform this operation dequeue, which is operation that takes the first element in the given queue and assigns it to this variable u, and removes this element from the queue. So we take the first node in the queue, and then process by this edges u, I mean the list. If I consider this kind of representation, so by these edges I mean the list of all edges that go from the given node u. Yeah, so we iterate through the edges going out of the given node, and v here represents for a given edge the node to which the given edge goes. So now we consider here in this loop an edge from node u to node v, and we check if this node is white, then the following is done, and if it's gray or black, so nothing is done with it. And so for white nodes, the covered v is now covered gray. The distance from v is set to distance of u plus 1. Yeah, so if current distance of u is 5, so distance of v will be 6. And for those node v, this node u is set as its predecessor. Yeah, and this node v is enqueued into the queue. Yeah, so we start with the initial node, and we take all edges going out of it, and check if we were not yet in the given node. We mark it gray, set its distance to 1, and put it into the queue. Yeah, and at the end, after all edges for u were processed, then u is covered back. We can yeah, so if we imagine how it works, we start with a node that has distance 0. Yeah, we take all edges going out of it, and by this we obtain nodes that have distance 1, that they are in the queue, and when we process them, and if we take look on edges that go out of this node, if they are if they go to some node that has not been processed yet, so that they will have distance 2, and will be put to the end of the queue. Yeah? So it's probably not so difficult to realize that we process at first all nodes of distance 0, then all nodes that have distance 1, then all nodes of the distance 2, then all nodes of distance 3, distance 4, and so on. And it's also the case that in every situation, those nodes that are gray are exactly those nodes that are currently in every iteration of this outer loop. These gray nodes are exactly those which are currently in the queue. White are those that were not processed yet, and black are those that have been already processed. And if we would like now to analyze the time complexity of this algorithm, so we can note that each node starts as white, or node S starts as gray, and it can become gray and they became black, but whenever it's put into the queue, it's never put into the queue once again. So it's clear that each node can go through the queue at most one times. So it's clear that this outer loop is performed at most n times, where n is the number of nodes. And when we process in this iteration of the outer loop, when we process node u, so each edge going out of it is processed exactly once. But as soon as this node u is processed, it will not be processed again. So also these edges will not be processed again. So the time how many times the body of this inner loop is performed, so it's in total it cannot be bigger than the number of edges of the given graph. So the total time that is, and it's also clear that this initialization, it takes time proportional to the number of nodes in theta n. So all these operations here in these parts outside of this inner loop are performed at most n times, and everything inside these loops could be performed at most m times, where m is the number of edges. So it gives us in total it gives us this time complexity theta n plus m, which is basically linear with respect to the time it takes just to read the information about the graph, just to read the list of nodes and list of edges. So in this sense, this breadth search is rather efficient. So here we have seen also the case when we have the running time expressed in terms of two parameters of n and m. Okay, let's go to another example of algorithmic problem of some other kind. It's problem of testing primarity of a natural number. So input is some arbitrary natural number, and output will be yes or no depending on whether the given number is a prime or not. So I will recall that primes are those natural numbers which are greater than 1 and have the property that they can be divided, they are divisible only by 1 and by itself. So here is a list of several primes, 2, 3, 5, 7 and so on. And it can be shown that there is infinite number of primes. So by the way, I will just mention, maybe I have already mentioned it in some lectures before, but I just recall that those problems where the output is yes or no are quite common. So for such problems we typically do not specify the output this way, that we would say output is yes if something holds and input is no otherwise, but we instead formulate the output as in a form of a question concerning the given input instance. So in case of questions we implicitly assume that the output is yes or no, or true or false, or 1 or 0. Just one bit of information is the output. So we have this decision, and such problems are called decision problems, when the output is yes or no. So using this kind of formulation, it could be represented by this. So input is a natural number and question is x a prime. So there are some very trivial algorithms that can solve it. The most trivial would be to try numbers from 2 to n minus 1 or x minus 1 and try to divide x by all these numbers. If for some of them we would have remainder 0, then we would know that x is not a prime, so we would return answer no. And if for each of them we would have some non-zero remainder of division, so the answer would be yes. It can be made slightly more efficient, for example, by taking of course we could analyze some special cases, the small trivial cases like 0, 1 and 2 as a special case. So we will concentrate on numbers which are greater or equal to 3, and we can also easily check if number is even. We just divide by 2, so we will concentrate, so then it's clear if it's greater than 2 and even, so it's not a prime. So if we concentrate on numbers which are odd and at least 3, so then we can try to divide them. It makes no sense to divide such number by even numbers, because it will clearly not be divisible. So we can try only odd potential divisors, and we can try numbers like 3, 5, 7, 9 and so on. And it's not necessary to go up to x minus 1. We can finish at square root of x. Because if it's divisible by some number, so the smallest of these non-trivial divisors must be at most square root of x. Because if it could be expressed, this x could be expressed like some a times b, for example. So this, where a and b would be, both of them would be greater than 1. So it cannot be the case that both of them would be greater than square root of x, because if I would multiply two numbers bigger than square root of x, I would obtain a number which would be greater than square root of x squared, which is x. So it would mean I cannot have a times b equal to x where both a and b would be greater than square root of x. So at least one of them must be smaller. In fact, either both of them would be equal to this, or one of them will be smaller and one of them will be bigger than square root of n. So it's quite obvious. So for example, if I would have some number which is approximately something close to 10,000, so square root of 10,000 is something about 100, and we just take those odd numbers, so we take just 1/2 of them. We would have about 50 iterations in this case. So it's smaller than 10,000. But if we take the number of bits that we need to represent the input number x as the size of the input, so let n be the number of bits. So we can know that the size of square root of x needs approximately 1/2 of n bits. If we would have some big number, maybe with thousands of bits, so this square root of x would have maybe 500 bits. And so basically the time complexity and we would take just half of them, but again it would be just some constant difference, not very big. So using this straightforward algorithm, even with this small improvements, is still exponential with respect to the number of bits. So it's slightly better than the completely trivial algorithm, but not so much. it's what is important, that this is still exponential, that the running time still grows exponentially with the number of bits. And but in practice, for example, in cryptography, in the in the design of cryptographic algorithms, it may be necessary to use some big numbers, maybe with thousands of bits that are primes, and some cryptographic algorithms require the possibility to generate such big primes. So this is a kind of problem that is not only of theoretical interest, but it's also important in practice. That we would like to have some algorithm that allows to test for big number whether it's a prime or not. So as I said, they play important role in cryptography. By the way, another question: even if we would be able to test for a given number if it's a prime, of course, it by itself it does not immediately allow us to generate big numbers. But in fact, it can be proved mathematically that the number of primes that primes are not rare, that they occur quite often in if we take numbers one by one. So the idea to how to generate a number that has 1000 of bits is just to generate them randomly, and we have quite big probability that after number of tries, which is approximately the number of bits we have, so maybe we have quite high probability that after maybe 1000 of tries, when we generate randomly a number which have that has 1000 of bits, it's quite probable that the probability is quite high of the situation where at least one of these numbers will be a prime. So this by this way, this allows us to generate big primes, and it may be so it may be interesting to ask whether we could have some more efficient algorithm, if we could have some polynomial time algorithm for testing primarity. And this problem is maybe quite surprisingly difficult. The question was open until 1003, when the first polynomial time algorithm was presented for this problem, and the time complexity of this algorithm was something like n to 12 plus some epsilon, where some epsilon is some small constant, so something bigger than n to 12, but it was polynomial. Later this algorithm, there were some improvements to using the ideas of this algorithm. Some another variants of this algorithm were found that are more efficient. It was later improved to something like big O n to 7.5, and currently the fastest algorithm for primarity testing is something like n2 big O n to 6. But this exponent 6 is still quite big, so it would take a lot of time for these numbers with thousands of bits. So what is interesting is that, in fact, which is much longer known from 70s, now from 1970s, there are known so-called randomized algorithms for this problem of primarity testing. Two best known algorithms of for these problems are called Soloway-Strassen and Miller-Rabin, according to authors of these algorithms. Both of them they are polynomial time, and both of them have complexity big O n to 3, so which is reasonable for use in practice for generating primes with thousands of bits. And but they have the property that they are so-called randomized algorithms. Yes, so in fact they are not correct algorithms in the sense we define it, that for every input the algorithm will always halt after some finite number of steps and give a correct answer. Yeah, so they will halt after a finite number of steps by the complexity is n to 3. So there is not problem that they will not halt, but the problem is that these algorithms could return wrong answers. And this randomization means this notion randomized algorithm means that the algorithm uses some generator of some random values. Yes, so some random number generator during the computation. So for the same input, there could be many different possible computations that could occur for the same input. So depending on which random values were generated during this computation, and the algorithm could produce different output depending on this random sequence that were used during the computation. And the output is not necessarily correct always. It could be wrong. It could produce wrong answer. So the natural question is, for what such algorithm is good for? Yeah, if it can produce wrong answers. So of course these algorithms that to be useful cannot be such that they will produce completely random answer. Yeah, they will just use random number generator and generate answer yes or no, depending on it. They have some important properties. I will not describe how these algorithms how they work precisely, but the property they have is that in case that the input x is really a prime, that the true correct answer is yes if it's a prime, so the answer produced by the algorithm will be always correct. They will always say yes, this is a prime. Yeah, so on primes they cannot produce wrong answer. On the other hand, if the number on input is not a prime, then there is some probability of wrong answer, and but the probability of this wrong answer is at most 1/2, yeah, at most 50% of probability that incorrect answer yes will be written. So whenever the algorithm obtains some input x, and whenever it will produce answer no, so it's again sure that this answer is correct, because this answer no cannot be produced for numbers which are really primes. Yeah, because for primes always number yes is generated, but the only case that can be wrong is that if the number on the input is not a prime, but the algorithm will incorrectly give answer yes, it's a prime, but in fact it's not. Yes, so but the probability of this is as most 1/2. So it may still seem rather word maybe why something like this could be used, how something like this could be useful, yeah, because 50% probability of error is rather high, yeah. But what is important, the idea is that we can decrease the probability of error arbitrarily by repeating the algorithm several times, yeah. So if we run the algorithm k times, so if in at least one, yeah, so we will run the algorithm with the same input several times, and whenever we will obtain answer no, we are sure that the given number x is not a prime, and we are sure that the answer is correct. On the other hand, when the input is a prime, and so it's sure that the algorithm will always gives answer yes, it will be correct. So in this case we will produce answer yes, but it can happen that if the number on the input is not a prime, but it's still after k runs, in each run will produce answer yes, so totally will give answer yes, it's a prime. But if we run the first time, so the probability of error of incorrect answer yes is one half. The probability, if we run it 2 times, the probability that it will 2 times give incorrect answer is 1/2 times 1/2, which is 1 divided by 4. If we run it 3 times, it will be 1/2 times 1/2 times 1/2, which is 1 divided by 8, and so on. Yeah. So in general, if we run it k times, the probability that the so in case if the input is a prime, it will surely give correct answer. If we would obtain answer no, it's again correct answer. So in the case if the number of the in the input is not a prime, but we always obtain answer yes, so the probability of this occurring is 1 divided 2 to k. Yeah. So if k is sufficiently big, then this number will be extremely small. It will be close to 0. Yeah. So for example, to give you some idea, if we would choose k, for example 100, so 1 divided by 2 to 100, because 2 to 100 is quite big number, so 1 divided by big number is very small number. So the probability of such error is in fact smaller than probability that the computer on which the program runs will be destroyed by falling meteorite. Yes, assuming that every 1000 years at least 100 square meters of Earth surface are destroyed by meteorite. So this probability of being hit by this would be bigger than error produced by this algorithm. Yeah. So in fact it's of course even bigger is the probability that there will be some hardware error on this computer. Yeah, that some part of the computer will have some misbehavior of the hardware or something like this. Yeah. So the real probability of the error is extremely small if we take this k big enough, and we can make it arbitrarily small, arbitrarily close to 0, but we never could made it equal to 0. Yeah. So it still be some non-zero very small non-zero probability that the algorithm could give wrong answer, but this could be extremely small, this probability of error. So it's useful in practice. Yeah. So in fact what is used in cryptography for testing primarity are these randomized algorithms, because they are more efficient than those polynomial time, but with higher degree of polynomial algorithms which ensure that the answer will be always correct. Yeah. but they are less efficient. So in practice we use those algorithms which are more efficient with small probability of error. So this was the example of randomized algorithms. Yeah. So now it slightly generalizes the notion what we consider a correct solution of the given problem. Yeah. So it's slightly different in case of randomized algorithms. I will now describe a very similar problem where input called factorization, where input is a natural number x, yeah, and let's take for simplicity number greater than 1, and we would like to find all primes such that the decomposition to primes, yeah, so primes such that if we multiply these primes we would obtain that x, yeah. For example, for number 24 we could express it as 2 times 2 times 2 times 3, and basically it means that we are able to find some we could test if the given number is a prime, so then we are finished. Just this prime is the only prime, there is nothing to do. But if we find out that the number is not a prime, so it would be sufficient for non-prime numbers to find some non-trivial divisor, which means some number which is greater than 1 and smaller than x, and divided the given number by this, yeah, because even for big numbers division could be done efficiently in polynomial time with respect to the number of bits. So division is something that could be done efficiently, and then we could proceed recursively on this divisor and this x divided by this divisor, yeah. So until only primes will remain, yeah. So what is interesting that there is no polynomial time algorithm known for this problem, polynomial time with respect to the number of bits of x. The especially hard case is the case where the number x was obtained by multiplying some big primes, yeah. So if I take two primes, each of them, for example, 1000 bits, and multiply them, so I will have x with 2000 bits. For such problem, it's difficult to find these primes from this was obtained, and some cryptographic algorithms are in fact their certainty of these algorithms, or they cannot be break, is based on the fact that there is no known efficient algorithm. Not even randomized algorithm is known for this factorization problem. If there would exist some efficient way how to factorize number, it would immediately mean that this then these ciphers could be easily breaked using such algorithm. Yeah. But as I said, so far no efficient algorithm is known for that. At least when we consider standard computers, yeah, as we know them, yeah, maybe there is this research area of quantum computers that work on some completely different principles, on principles of quantum mechanics, where in fact they allow to test many cases in parallel. Yeah. So using quantum computers, there are proposed for these special kinds of computers, there are proposed efficient algorithms, or there is a known efficient algorithm for factorization. Yeah, but so far these computers are not powerful enough to process such big numbers. Yeah, so as far as I know, this still cannot be done in practice. But this is maybe some possible way how such ciphers could be breaked in the future, maybe using such devices as quantum computers. Let's go to another example of a problem where known efficient algorithm is known. The problem is called independent set problem. An input in this problem consists of an undirected graph and number k, and question is whether there exists in the given graph an independent set of size k. Yeah? So for example, such graph and number k is 4. Independent set in a graph is a set of nodes such that none pair of nodes in this set is connected by an edge. For example, in this particular graph, the answer is yes, because there exists this independent set of size 4. So we have these 4 nodes when none of them are of these selected nodes are connected by edge with other selected node. Maybe one simple idea how we can remember this problem. We can the statement of this problem, the formulation of this problem. We can imagine, for example, let's assume we would have consider animals in a zoo, and there would be maybe some enclosure, some pavilion where we would like to have several kinds of animals. And these kinds of animals will correspond to the nodes of the graph, and 2 nodes will be connected together if these 2 kinds of animals cannot be in the same enclosure. Or for example, we cannot take lions and zebras together because lions would eat zebras. So they cannot be together. But some kinds of animals they could be. So the question is if this is the total number of kinds of animals we have, and we mark by these edges which cannot be put together, and we would like to put as many as possible of them together. So for example, this can be with this and this. So either it can be formulated as an optimization problem where we have just graph and no number, and the question is to find the biggest possible independent set, or it can be formulated as a decision problem where we have also the number k, and the question is whether there exists some independent set of size k. So it's obvious that if we could solve this optimization problem, then we could solve this decision problem. And you can think also about the possibility that if there would be the efficient algorithm for this decision problem, then in fact we could solve efficiently also this more general optimization problem. So let's consider this simpler decision problem. Just to give so I have already given example of instance where the answer is yes, and here is an example of where answer is no. You can try yourself that you cannot select 5 nodes in such a way that none of them would be connected by an edge, and it's rather obvious that we could just because these independent sets are subsets, and set of n elements has 2 to n subsets, so we could use some trivial brute force algorithm that would just systematically try all subsets. So it's clear that we would generate all subsets and check if the given subset is of size k and is independent. Yeah, for each subset we would just check all edges, and we would check whether there is some connected pair of nodes in the given subset or not. So whenever we find some subset of size k which is independent, we end with answer yes, and if we check all of them and none of them is independent, so we return answer no, that does not exist. So this is a trivial algorithm. Yeah, in fact it's not necessary to generate all subsets but only subsets of size k, but the number of subsets of size k is n2k, this combination number. But in fact this value is not much smaller than 2 to n, and then the number of in particular if this k is close to n divided by 2. Yeah, so for example if k is n divided by 2, so it can be shown, we will not do it formally now, but it's at least 2 to n divided by n. Yeah, so it's not so much smaller than 2 to n. So such brute force algorithm is not very efficient if the graph will be big. So of course we can think about some improvements to this brute force algorithm. It's not necessary to try all these possibilities. Yeah, we can have some more clever way, but still there is no known so as I have said, yeah, so we would use this brute force algorithm. It will have this time complexity to theta n, so exponential time complexity. But what is interesting here is that there is no known efficient polynomial time algorithm for this problem. Yeah, despite many attempts to obtain such algorithm, and the reason is that this is example of so-called NP-complete problems. Yeah, so we will discuss these NP-complete problems on the next lecture, and these are problems that typically for them it's quite obvious that they have a exponential time solution. There exists algorithm with exponential time complexity for these problems. For none of these NP-complete problems there is no known polynomial time algorithm. On the other hand, it's not known whether it's not known any proof that would show impossibility of constructing of such polynomial time algorithm. And what is even more interesting is that if somebody would succeed in finding polynomial time algorithm for at least one of these NP-complete problems, it would immediately give us polynomial time algorithms for all other NP-complete problems. And on the other hand, if somebody would prove that for at least one of these NP-complete problems that it's not possible to have a polynomial time algorithm for this problem, it would imply that there cannot exist polynomial time algorithm for any of these problems. Yeah, so but none of this is known, so this is open question, and in fact it's one of the biggest open questions in complexity theory in general. Yeah, in the study of algorithms and complexity of algorithms. This is this is probably the biggest and most important question which is still open, which is not known. Yeah, so we will discuss about these NP-complete problems on the next week. Yeah, so that's all for today. So thank you for your attention and goodbye.